In this video, we are going to look once again at binding energy, but this time define a quantity called binding energy per nucleon. We're going to use the binding energy per nucleon to look at the stability of the nucleus and the relationship between the two. And then we're going to calculate, using the binding energy per nucleon, the amount of energy that's given off when there is fusion, but this time we're also going to look at fission. The definition of binding energy is the energy released when a nucleus is formed from its constituent nucleons. Now this is what happens in fusion. Alternatively, it is equal to the work required to completely separate the nucleons. So this is fission. Binding energy is the energy equivalent of the mass defect. Now, binding energy per nucleon is that number divided by the number of nucleons it contains. And it is a measure of stability. The more binding energy per nucleon, the more stable the nucleus is. So let's have a look at helium-4. The amount of binding energy for helium-4 is 28.6. The amount of binding energy per nucleon would be 28.6 divided by 4. That gives you a value of 7.15. Similarly, nitrogen-14. If the binding energy for nitrogen-14 is 101 megaevolts, divide that quantity by 14 to give you the binding energy per nucleon, 7.22. The more binding energy per nucleon, the more stable the nucleus is. The more likely a reaction is to happen. If a nucleus needs a lot of energy in order to break it or to make it, it's very difficult for it to then gain access to that energy, and it's less likely to happen. Here we have a graph which demonstrates the rate of stability for all the elements in the periodic table. So not really a rate of stability, it pretty much gives you a measure of the stability for the periodic table. Starting with, if we look on the x-axis, which reads number of nucleons, we're starting off with the smallest, which is 1 proton, the simplest hydrogen isotope, going up to the heaviest nuclei, which we will be considering, which would be a uranium isotope. This one is uranium-238. All elements go on here. However, in the IB, the main focus is on 3 elements. On the y-axis, we have the average binding energy per nucleon. So what the IB wants us to focus on is the small elements, like hydrogen, which have a low amount of binding energy per nucleon, iron, which has the biggest value, and uranium, which is basically the lowest in this section. Now, these 3 symbolize the 3, or represent the 3 important areas on this graph. The first area here shows very small nuclei, which are very unstable. Why are they very unstable? Because they have a low binding energy per nucleon. These undergo nuclear fusion. They fuse together to create larger nuclei, which have greater stability and greater binding energy. Iron is the most stable, and you should be able to identify its binding energy per nucleon. This peak is approximately at 9. You should remember that. This area here is uranium. Larger nuclei are less stable. They undergo nuclear fission to become more stable. So this area here is where energy is lost due to the size of the nucleus. Before we go any further, I'd like you to go to the booklet and answer question 1, 2, and 3, and then continue with the video. Now, once you are clear on the definitions, the difference between binding energy per nucleon, and you can label the binding energy per nucleon graph, we're now going to look at some calculations. We're going to calculate the amount of energy given off. Now, as an element or a nucleus changes from having a smaller size to a larger size, its binding energy per nucleon changes. There is an emission of energy. Now, the amount of energy released is the difference between the binding energies of the products and the reactants. And first, you need to have a very clear idea of what those are. This is a fission reaction, the bombardment of uranium-235 with neutrons. This makes the nucleus, the uranium nucleus, unstable, and it breaks to form some more elements, two different elements, and 3 neutrons are released. This is an example of a fission reaction that could take place in a nuclear reactor, for example. Now, the reactants are what we find before the reaction takes place. So, neutron and uranium, these two are reactants. These are all the products of the reaction. They are what happens afterwards, after the reaction takes place. So, in order to work out this energy value, the amount of energy left, we are going to work out the difference between the binding energies of the products over here and the reactants. So let's have a look at a question. In a nuclear fusion reaction, a nucleus of deuterium, hydrogen-2, fuses with a nucleus of helium-3 to then produce helium-4 and a proton. So here are the binding energies, and they are listed below. Now, the amount of energy released is the difference between the binding energies of the products and the reactants. So let's identify the products and the reactants and then calculate their binding energies. The reactants are hydrogen-2 and helium-3. The products are helium-4 plus the proton. Now, the binding energy for each nucleus must be calculated from the binding energy per nucleon. Note that hydrogen-2 has 2 nucleons, and so the total binding energy would be 1.112287 times 2. Similarly, helium-3 has 3 nucleons, and so the binding energy for helium-3 would be 2.5 and so on times 3. Helium would be 4 times this value, and note the proton is on its own, so there is no binding energy here because we are not binding the proton to anything. Okay, so here you can see the difference calculation. Binding of energy of helium, which is 4 times this value, minus the addition of the reactant's binding energy. And then your difference would be equal to 18.353043 megaevolts. Now, can you please try question 6a? Finish doing question 5a, which is this question on the booklet. Try it yourself, see if you get the same answer, and then go straight on to question 6a. So far we've worked out the amount of energy given off when a single nucleus or a set of single nuclei either fuse or there's a fission reaction. And we're doing that by finding the total binding energy per nucleon times the number of nucleons, and then we're working out the difference in binding energies for the products and the reactants. Now, what happens when we are trying to apply this to an amount which is more tangible? Say, for example, a kilogram. We have a kilogram of uranium. How much energy will that give us? For that, we need to use the idea of Avogadro's constant, the mole, and also the molar mass. To remind you, the molar mass is the mass of 1 mole of a substance. And 1 mole of a substance is 6.02 times 10 to the 23 atoms. In this case, it would be nuclei. We're not dealing with molecules or atoms, we're dealing with nuclei. So if we want to find the amount of energy given off by 1 kilogram, we start off by finding the amount of energy given by one nucleus, right? Or one reaction, just like in the previous question. Now, once we have the amount given off in one reaction, then the next step is to find the amount of energy given off if there's 1 mole of the substance. So that would be 6.02 times 10 to the 23 times the energy given off by one reaction. And what you've got there is the energy given off by 1 mole of the substance. Now, if you have the molar mass, you will know how much mass gives you that energy. And then you simply work out for the quantity in the question, how many moles fit into that mass. And you do that using the molar mass. If you work out the ratio of mass to molar mass, as it is here, then you'll know how many moles fit into your mass, right? Let me apply this to the previous question, which goes on after you've worked out the energy in one reaction, then goes on to ask, well, if you have 1 kilogram of helium, if you make 1 kilogram of helium and the molar mass is 4 grams per mole, how much energy will be released in joules? Well, you find out how many 4s go into 1,000, and that tells you how many moles there are in a kilogram. Then you multiply that by Avogadro's constant, and you multiply that by the amount of energy given off by one reaction, which is what you worked out before. And this gives you the total energy. Try finishing this question off, and then go on to finishing off the rest of the worksheet.